Hi everyone, I'm Murli, and in this video, I'm going to be talking about NODAGS-Flow, a nonlinear cyclic causal structure learning framework. This work was done in collaboration with Romain Lopez, Rahul Mohan, Faramarz Fekri, Tommaso Biancalani, and Jan-Christian Huger. Causal understanding of real-world system is a crucial aspect of how we understand the world around us, and it's also crucial for prediction of these systems under potentially unseen interventions. With a few notable exceptions, majority of causal discovery methods rely on this assumption that the underlying graph is a directed acyclic graph. That is, they don't allow for directed cycles. While this assumption is helpful in regularizing the search space of all candidate graphs, it is not very realistic in practice. A popular example, which is common in economics, is that of the supply and demand dependency, which is cyclic by nature. Unfortunately, such systems are harder to study, and it's even more harder to obtain meaningful data to test causal discovery methods on. But more recently, with some of the advances in biology, have allowed for performing large-scale interventions on gene regulatory networks, which enable us to develop causal discovery methods which are capable of learning cycles and also being able to test them on real-world datasets. Here, we present NODAGS-Flow, a novel framework for causal discovery that allows for cycles as well as flexible nonlinear causal relations. NODAGS-Flow is based on maximum likelihood estimation while utilizing contractive residual flows. NODAGS-Flow is differentiable, consistent, and can handle both observational as well as interventional data. The proposed optimization program avoids any parameter tuning for constrained optimization, as is common in most algorithms of this class. Through experiments on synthetic and real-world data, we showcase the benefits of the proposed method. The problem setup can be summarized as follows. Let G be a directed cyclic graph that represents a discrete dynamical system with observations at time t taken over all of the nodes in the graph. The causal dependencies between these nodes can be represented by a series of structural equations where each node xi is some potential nonlinear function of its parents and an intrinsic noise variable epsilon I. These structural equations can be grouped together to obtain the vectorized form as shown here, where the observation at time t is dependent on the observation at time t minus 1. Under some conditions, these systems attain a steady state where the observations become the solution to a fixed point equation given the intrinsic noise terms, and the one-to-one map between the intrinsic noise terms and the observations is given by identity minus f. We call such a state the equilibrium state, and always consider that the data is measured from the equilibrium state of the system. In general, it is not always necessary that such an equilibrium state is attained by the system, and hence we make the following assumptions in order to guarantee that the equilibrium is achieved. We start by first assuming that there are no latent confounders, that is, all variables that exert a causal influence are measured, and we also assume that the distribution of the intrinsic noise variables are known up to its family. And finally, we assume that the forward map identity minus f is invertible and that both the forward and the reverse map are differentiable. These assumptions also guarantee that the data likelihood can be computed. Under the assumption stated previously, we want to think of this problem within the framework of differentiable causal discovery. Differentiable causal discovery methods have gained significant popularity in the recent years due to its flexible nature and the ability to learn nonlinear causal relations. DCDI is one such state-of-the-art technique developed by Brulard et al., where the structure is learned by maximizing the data likelihood along with a sparsity regularizer by restricting the search space to the space of DAGs. While this method has several advantages, the main drawback here is in restricting the search space to the space of DAGs, as the DAG constraint can be quite expensive to compute for large graphs, and in addition it requires augmented Lagrangian based solvers for optimizing the objective, which can make the overall optimization problem quite complex. And moreover, the data likelihood that's computed is the true data likelihood only when the underlying graph in consideration is a DAG, which may not always be the case during the learning phase. In contrast, NODAGS-Flow does not require any augmented Lagrangian based optimization techniques because we don't restrict the search space to the space of DAGs. making the overall optimization problem much more easier to solve. And the data likelihood that's computed is always the true likelihood, no matter what state of the learning process we are. The main trade-off here, however, is in the complexity of computing the data likelihood, which could sometimes be quite expensive. And we later address how we reduce the complexity of computing the data likelihood in order to make this method more practical. Going back to the problem setup, given the structural equations and the assumptions, the density of the observations is given by the following equation, where J sub ID minus f of x is the Jacobian operator of the forward map, that is identity minus f, evaluated at the observation x. Thus, given a set of observation, the log of the data likelihood is given by the following equation, where the main complexity in computing the data likelihood arises from the second term in the summation, that is the log of the determinant of the Jacobian, also called log det Jacobian. And this is because in order to evaluate this, we need gradient calls, which in the order of d square, where d is the number of nodes in the graph. Before we talk about how we evaluate the log determinant of the Jacobian, we first provide some details about the causal mechanism. The causal mechanism is modeled using contractive neural networks, where a contractive function is nothing but a Lipschitz function whose Lipschitz constant is less than 1. Additionally, we use input dependency mask, which is a binary matrix sampled from Gumbel's softmax distribution, shown in the figure, which explicitly encodes the parent-child relations. The contractivity of the neural network is enforced by rescaling the neural network weights every time the weights are updated. Thus, the forward map going from the observations x to epsilon, that is identity minus f, forms a contractive residual normalizing flow network due to the presence of the residual connection in the forward map. What's more, the contractivity of the causal mechanism guarantees the existence of the inverse of the forward map, and the inverse can be computed using fixed point iterations. We now outline how we compute the log determinant of the Jacobian. The methods outlined here were inspired by the works of Beherman et al. And Chen et al. We start by noting that the log determinant of the Jacobian has the following power series expansion, which only depends on the trace of the powers of the Jacobian. Now this already has a much lower complexity compared to naively computing the determinant of the Jacobian, as trace only requires an order of d gradient calls, where d is the number of nodes in the graph, and the power series is guaranteed to converge when f is contractive. Now, in practice, we restrict the number of terms in the power series to a finite number. This complexity can further be improved by using the Hutchinson trace estimator, where the trace of the Jacobian is estimated using the following equation. And to evaluate this, we only require a single gradient call, making it much more efficient than before. And finally, while restricting the number of terms in the power series to a finite number could potentially introduce some bias in our estimate, and in order to overcome that, we randomize the number of terms involved in the power series by sampling it from a distribution and reweighting each term in the power series according to the distribution with which we sampled the number of terms from. Thus, we obtain the final estimator for the log determinant of the Jacobian, which does not have any bias and it can be computed efficiently. So far, we've only considered contractive causal mechanisms. While this is sufficient for the invertibility of the forward map ID minus f, it is strictly not necessary. This is indeed the case for DAGs, where the figure over here shows an example of a non-contractive DAG which attains equilibrium in 3 time step, but contractivity is still a requirement for efficiently computing the log determinant of the Jacobian. And hence, to tackle this issue, we introduce preconditioning terms into our model, and using the preconditioning terms, it is possible to represent a non-contractive causal mechanism via a composition of the preconditioning term and a contractive function when the underlying graph is a DAG, and also efficiently compute the log determinant of the Jacobian for this non-contractive function, which is formally stated in the proposition shown over here. This results in the final objective shown within the orange block, where we have the data likelihood, including the preconditioning term that we introduced in this slide, along with a sparsity inducing regularizer. This is optimized with respect to the parameters of the causal mechanism and the dependency mask. The final objective is amenable to stochastic gradient based solvers, and in our experiments we utilize Adam optimizer to solve the final objective and find the best model parameters. NODAGS-Flow is also capable of handling interventional data, and in this work we only consider surgical or perfect interventions. That is, the incoming edges to the nodes that are intervened are removed in the intervened graph. And the structure, given a family of interventions, the structural equations of the intervened nodes are purely governed by these new random variables epsilon I tilde, whose behavior is governed by us. And the structural equations of the purely observed nodes remain unchanged from the observational setting. And similar to last time, we can combine these structural equations to form the vectorized equation shown over here, where U here is the diagonal matrix with ones corresponding to the purely observed nodes. And similar to last time, the density of X under the interventional setting is given by the following equation. And the important thing to note over here is it has the same underlying form as the density in the observational setting, and thus it can be readily incorporated into our final objective. Under a restricted setting, NODAGS-Flow is probably consistent. That is, when the structural equations are linear and the disturbance is Gaussian, the graph estimated by NODAGS-Flow is identifiable to the ground truth graph, assuming that the global minima is reached, up to a notion of quasi-equivalence extended to allow for interventions. Now this is formalized by the theorem shown here. We now compare the performance of NODAGS-Flow with the existing state-of-the-art causal discovery methods. A summary of the baselines is shown in the table in the top left. Of the chosen baselines, DCDI is the current state-of-the-art when it comes to learning nonlinear DAGs, and LLC is the current state-of-the-art when it comes to learning linear cyclic graphs. A total of 4 different experiments were performed where we varied the structural equations to be either linear or nonlinear, and the underlying causal graph to be either a DAG or a cyclic graph. In all of these settings, the training set consisted of single node interventions over all of the nodes in the graph, and the testing set consisted of unseen 2-node interventions. In order to measure the performance of these methods, we use structural Hamming distance, which measures the accuracy of the estimated graph to the underlying ground truth graph, and the holdout negative log likelihood, which measures the predictive capabilities of these methods over unseen interventions. And as seen from the figure on the right, we can see that NODAGS-Flow performs much better than the baselines when it comes to recovering cyclic nonlinear graphs, and is competitive with the existing baselines over all of the other experimental settings. We also compare NODAGS-Flow with the baselines on a real-world gene perturbation dataset. The dataset under consideration was taken from Frangi et al., which contains gene expressions from over 200,000 melanoma cells split over 3 different groups: control, co-culture, and interferon gamma. And each cell measurement here contains gene expressions for over 20,000 genes in the human genome, but due to practical limitations we restricted to a subset of 61 genes. Due to the lack of a ground truth graph to evaluate the causal discovery methods, we rely on evaluating these methods on its predictive capabilities over unseen interventions, and thus we employ holdout log likelihood and a mean absolute error over the unseen interventions as error metrics to measure the performance of these methods. And as seen from the figure, we can see that NODAGS-Flow is able to outperform all of the baselines over all of the groups of the dataset, thus showing that it is indeed beneficial to learn cycles for real-world systems. In conclusion, we presented NODAGS-Flow, a differentiable nonlinear causal graph recovery framework, which allows for cycles and is capable of handling interventional data. It is based on maximum likelihood estimations while not requiring any parameter tuning for constraint optimization. We employed contractive neural networks and residual flows for efficiently computing the data likelihood. And then through synthetic and real-world experiments, we showcased improved recovery performance. Thank you.